Welcome back to the Automation Podcast, the world's #1 industrial automation product and technology show. Thanks to you, our audience of highly skilled automation professionals. Thank you for being a member of our audience, and thank you for tuning back in this week. Now, if you do enjoy this series, please consider giving this episode a like, as it's the only proven way for us to grow our audience and find new vendors to come on the show. Now, with that said, if you're new to the show, my name is Shawn and my company is Insights in Automation. And each week I invite a new guest to come on the show to talk to us about their industrial automation products and technologies. And during the show, I play the role of the audience, asking questions I think you might have, as well as adding my own comments and questions based on my experience in the industry. And given that over a quarter of our audience listens to the show, if our guest is using visuals, I'll try to call attention to any of the details that I think the listen-only audience may want to know about. But this week, there's going to be no visuals because I'm interviewing Ronnie from Micropsi. Very interesting company and products. So without further ado, let's learn what Micropsi can do to help you and your facility. Ronnie, welcome to the show. It's great to have you on. I know you're here to talk about AI and vision and robotics. 3 topics we cover a lot in my content. But before we actually jump in and start talking about specifically what you and your colleagues do, could you please first introduce yourself to our audience?
Yes. Hi, Shawn. Thanks for the invitation. My name is Ronnie Vuine. I am one of the founders of Micropsi Industries. We do a software that controls robots and makes them do things that otherwise they wouldn't be doing. So you would have to use a human instead of automation for it. I'm 45 years old, to my own perpetual surprise. I have a background in computer science and philosophy, actually, which was a bit of a random choice I made in high school that I would study these subjects. And then at university, I discovered there's very few intersections where sort of you meet the same people. And the intersection is, one of the intersections is AI. So very early on in my studies, I was sort of became part of a group of people who thought about how to make systems intelligent, or more importantly, what even is intelligence, right? What's this weird property of some systems that changes everything when it shows up and makes everything more awesome? How do you understand it and how do you build it? Because if you know how to build it, you know what it is, right? So that's been there was a group of people who thought about these things at university, and from that group of people, a bunch of things happened. One of which is Micropsi Industries, the company that does that. We're not originally robotics people; we're AI people. We were always interested in systems that don't know what they will be doing when they leave the lab. So these systems that learn what to do in the field, and then looking for meaningful things to do with that. We sort of stumbled upon robotics, where we realized, oh, wait a second, in science fiction, robots do all sorts of things. In actual factories, they move from A to B, and you need to know A and B. And sometimes you've taken a measurement for where B is with a camera, but that's as far as it will go. Sort of the real sensor-driven real-time motion for robots, which would obviously be useful for many things in assembly or testing, nobody's doing. And then I had this moment at a car factory in southern Germany, where I was just walking around pointing at people and saying, why is this a high-paid Bavarian and not a robot? And then they told me, and I said, oh, I think we can make that happen. We can build what you would need to automate this. And that's how the company and how the product came about. Company's been around for 10 years, 6 of which were research, and then 2 of which were dealing with a certain pandemic. And then after that, we've been out there selling and scaling the system.
It's really interesting that you say that. And I think some of the people listening are like me too, where we think about why, like the why. Like whenever I use software, and again, going back to my Apple II and my Commodore VIC-20, why did they put this button here? Why is this feature hidden? Why is this setting not something and there's a lot of that in automation too. And it's very frustrating when somebody comes over and says, well, can't you make it do that? And it's kind of like and I would always tell them, it's like, well, can't you just make your own vehicle from scratch? Like, You want a Ferrari? Just make one, right? It's that kind of silly. It's like, yeah, the programming that you need to do and the information you need to have can be mind-boggling to do some tasks. And of course, we have a lot of integrators listening in who actually have to come up with that code, and we have a lot of users who actually get to see that code in both its probably best and worst iterations. But so I think it's very interesting because in robotics, right, it's just not as easy as like a lot of systems are just A and B, right? A and B, A and B. And, one of the things we've seen with AI coming out is, in the past we would teach a photo eye, we'd have a self-teach feature in it. We'd put up the good product, self-teach, bad product, self-teach. And that would get us maybe 80% of the way there. Not, we'd have to do a lot of tweaking. But today with AI and like vision, a lot of times we show it 3 or 4 products and it's good to go. So I'm very interested to see how you guys are implementing these technologies today and what you're doing.
Yeah. So first of all, what does the product actually do, right? It gets your tool, whatever your tool is, you're free to choose, to where it needs to do work on the end of a robot, right? So we bring the tool. If the tool does an assembly, right, you take a part and you make an assembly step somewhere. You plug something in, you click something in, you any, be it a cable or be it a plastic part or be it a part that you put into a machine where some future additional process step happens. Or your tool is sort of a probe and you do some sort of measuring, an electrical test, a chemical sort of a sniffing test is an application we've done. So essentially we get the tool where it needs to be. And we don't do this from a library of known tasks, because in manufacturing it doesn't work, because many of the tasks that robots driven by our product are doing it exist in maybe 5 factories, because the parts you're dealing with or the problem you're dealing with is very specific to this industry or even this manufacturer. So the key thing is the product is trainable by humans. And to sort of my standard routine to explain what the difference is to what you're already familiar with. So I've seen cameras. They tell me where to move the robot as well. So what's the difference here is, think about you want to plug in a cable into a phone. Maybe you've just made the phone and you want to charge it. So what traditionally you would have done in that problem, you would have gotten a 3D camera, which is already a fairly expensive system. And a slow system. It's really expensive, it's fast, but typically it takes 2 seconds or so. And it gives you a point cloud. And then you have a 3D model of the phone. And then you fit the phone into the point cloud that you get with some fast sort of fitting algorithm. And it gives you a precise position of the phone in 6D, right? 3 space dimensions and 3 rotations. And then you have a trajectory generation algorithm that the robot typically brings, and you make a single delivery motion with the robot. So if you got the measurement wrong by half a degree, that motion will fail and you'll scratch the phone, and you'll need to turn out the red light, and the engineer needs to come and save the robot from what is just done. So everybody hates these systems because they're brittle and they're fragile and they're hard to tweak, and you keep iterating on individual parameters and list all the exception cases, and then maybe your time of flight based and sunlight is a problem. So it's a very, very brittle system. People don't like to do this type of stuff. So it's essentially you only do this if it's your last option. And famously, in car manufacturing, a certain American electrical car maker has bought hundreds of robots, made very strong statements about alien dreadnoughts and light out factories. And now they're making these cars in tents with humans. I've been to the tent, so it's still there. So, right, if you get this wrong, then you're not getting anything from the automation. In fact, you're getting yourself in deep trouble. Okay, now I am a human and I'm extremely good at plugging in cables. I do this every day, and it's not a problem for me at all. Why am I? And I don't even have a measurement in 6D to a 1/10 of a degree precision in rotation in base coordinates of my left arm. And yet I'm so much better. Why is that? How is that possible? What's the difference? And the difference is I am not, as a human, solving the extremely hard engineer problem of taking a super precise measurement. I'm just plugging in. And when I'm saying I'm just plugging in is what I'm doing, I'm moving towards the goal in a very imprecise manner, and I make small corrective motions as I get closer. And this actually gets easier the closer I come because I see what the corrective movement is more easily because I'm closer, right? I don't need to do this from 50 centimeters difference. So this precise capability to correct a robot motion as I approach the target and get all the stability and predictability and reliability benefits and precision benefits from doing it that way, we give to industrial robots. And the catch is we don't do it for just cables, but for anything you can demonstrate to a robot by showing it the target position or showing it the actual motion it would need to make. So you can train the system yourself with any tool, with any camera configuration on the wrist or statically outside that would get the robot to where it needs to be. And you typically use this for the interesting bits of a larger robot program. Right, so you write your standard robot program. The robot moves very fast through the boring parts of its motion, right, from A to B. But then for the variance that you have, even in a car factory, where the car never exactly stops at the same point, or that you have because your part is soft and jiggles about, or because you have some vibration that never leaves anything in there, or because the part you're handling has been made by hand by a human in the step before, and you don't know exactly what it's shaped like. So all these variances that you inherit from the product or from your logistics or whatever else for your suppliers, you inherit some imprecisions. And our product helps you to do away with them and do it in a super reliable, super robust, and easy to train on site by a human fashion. Now answering your question, how do we even do this? How do we make it so robust? Part of the trick is neural networks. Some of the robustness you get from neural networks who are unreasonably good at interpolating between examples you show, right? They just work very well at this. So you show one extreme and the other extreme and one thing in between, and everything in between that will generally work. So if you cover the state space with examples well, everything in between, if you're working with neural networks and you know what you're doing, will work. You get some of the robustness from the real-time properties because you do not make a single measurement that needs to happen at the highest possible precision. But you get lots and lots of chances to, even if you got it slightly wrong in the previous step, to get it more right in the next step. And the chances that you'll be right increase as you get closer because it's easier to see where you go. So we sort of, one abstract way of explaining what we're doing is we give machines the autonomy they need to deal with the slight variances you encounter, but we do it in a fashion that is constrained, so the result stays predictable and it stays completely compliant. It does exactly what you want it to do. We're still doing automation, right? It should not get any ideas. We want it to do this thing and this thing only, and we want it to do it for 20 years. In the ideal case, and where we're really making money off the line. Yeah. Right. So the autonomy to deal with the variation under those inherited constraints that any reasonable machine needs to have is sort of the magic that we bring to the factory.
Yeah, and so I wanted to ask you a question as you're explaining what you do. I'm thinking closed loop systems. So when we have a servo control system, we're constantly monitoring the feedback to make sure things are happening the way we're commanding them to happen. And we can adjust on the fly if there's a little bit more, if we need a little bit more torque to meet, where we need to be and at what time we need to be there. This motion control systems out there that do that for servos. And there's systems that do that for robots too. But it does sound like your system stays connected and is a closed loop system. Am I correct? Or is this like a teach once and then download and you go away?
So the actual control signal that the software generates is closing a control loop via a camera. So this is essentially, I mean, for the veterans and the researchers in the audience, this is neural network trainable visual servoing. So you have a closed loop system that generates a sort of closed loop signal through a camera, an RGB image from actually two cameras in most cases. So it isn't as fast as the loop you'll get from the actual servo control that's inside the robot. And it sits on top of that, right? We still just execute through all the normal control loops that the robot already have. By the way, inheriting all the robot's safety configuration and properties through that. So there's no shenanigans that we can do from neural networks that the robot can't execute. But yeah, while we're on, which again isn't the whole application, it's typically some skills that the robot needs to make complicated parts of the overall application. The control flow goes from the robot controller, which does essentially position control on the servos, to us, who will have a different control loop on top and generate the targets for the servos in a correcting fashion in a closed loop from the camera images. Yep, that's what's going on.
So a standard robot, you would tell it go point A to B, and you may say go point A, B, C, D, E, F, G, but it has no eyes.
Yes.
It just goes exactly where you tell it. And the trickiness of putting a camera in is, and I know a lot of the old timers who've been doing this longer than I do, remember back, computer vision in the 80s, it was extremely difficult and you'd never wanted anything to change. Like the part have to come down the conveyor in the same exact orientation every single time. I'm over exaggerating, but that was the gist. Like lighting changes or distance to the part changes and it messed up
Spec
everything
on
with
the
the computer
lens,
vision.
it breaks. Yeah.
Exactly. So what you're doing is you're not only giving the robot eyes, but you're giving it the ability to address variations by using the neural network. And would you mind, there may be some of our audience out there who they hear AI, they hear neural network, but they may not know what neural network is at its core when you say that, right? I mean, people think a computerized brain, but really scientifically, how would you describe a neural network?
So a piece of math that isn't actually that complicated. So what this system does is you have a camera image, which in reality is three arrays of x times y pixel values. So that's just a bunch of numbers. And then you have a large table of coefficients, numbers that look random if you look at them. And then you just multiply a bunch of these tables onto the values you get out of the camera, onto the pixels. So this is just cross products, right? So you multiply this. Every table of values that you multiply onto the image is a layer in the neural network. That's what that is. And you do a sequence of these multiplications of coefficient tables, and then out comes a 60 vector, which is the displacement for your tool. That's what you send for execution to the robot controller. Right, so that's really all there is. We do this 15 times a second. So 15 times a second, we'll get an image, multiply all these tables onto it, get a displacement vector out of it, and send it to the robot for execution. Now, the interesting part is how do you come up with the random looking numbers in the tables? That is the magic, right? Because if they're actually random, your robot will do nonsense. But if you know what you're doing, it will do exactly what you've taught it to do. And you've taught it what to do by recording examples of motions it's supposed to make or positions it's supposed to go to. So it knows what the desired situation looks like in the camera. And it knows what motions you taught it to make to get there by jogging it there or by guiding it by the nose, right? You literally grab the wrist of the robot and there's a force torque sensor connected and then you guide it through that motion. If you want to teach an actual motion, not just a position. So, and this data gets recorded by the system at deployment time. So this is videos of what the world looks like, including the first frame, which is the situation you want the system to be in, and motions that correlate to the video. right? So it's the same time series. You just have a video and the motions that the robot make while that video was generated, and you send this pair of motion data and video data to our cloud where a bunch of magic happens, and back come the coefficients that you then can use to multiply on your camera image, and then the robot will do the right thing. So that's really all there is going on. The magic that happens there is, of course, where our core know-how is. How do you use this data to train neural networks in a fashion that it doesn't just work once? Right? Everybody who's even studied control at university has used a neural network to do something like that. And then everybody who's done that knows, yeah, I play a bit with the hyperparameters, and then maybe there's a layer it needs to be a bit bigger. So you play around with that, right? We don't have these options in this product because no human sees the data. So when that data gets recorded on site in your factory and then sent for processing, we don't look at it. There's an algorithm that takes that data and 45 minutes later comes back with coefficients that you can run on your robot, and it will do the task, and it works every single time. So this is where the magic happens. It sometimes works slightly better or slightly less. And then you need to add some more data because you've not shown things that happen in the real right? So typically this is iterative. You do 10 examples, and then it generally works, but there are some situations, light situations, material situations, orientations. Some of the variants you haven't covered, you haven't shown, so you haven't given the neural network a chance to interpolate to this part of the state space. So you realize that trying the system out. So you add some more data, you do this cycle again, and at some point you'll covered everything that actually happens. And then the system will be robust against all the things you've shown and everything in between and all the combinations of these things.
Yeah, and that's important. A lot of people who've not used a system like this may not understand. You really have to cover the what's going to happen. You really have to cover, like you said, lighting changes. A lot of time, even simple sensors will be thrown off by glaring light in the morning when the sun's coming up. And even my car, the cruise control, the adaptive cruise control, if the sun's hitting it just at the right angle, it'll give me a braking warning because it thinks somebody's right in front of it. And that's why you do have to cover all those different situations. So I think your example of plugging a charger, especially the little ones we have now, into a phone, and where the phone may not always be in the same exact millimeter by millimeter spot, is a good one. What other application examples could you share with the audience? Like, if you have a situation like this, give us a call. Let's talk about your
Yeah.
application. Like, I'm sure you've seen, I know I don't want to talk any customer names or, any, I don't want to ruin any NDAs, but what kind of type of applications out there in manufacturing or other applications do you think your solution is a good fit for?
Yeah, let me start in the abstract, and then I'll do a couple of very concrete examples of stuff we've done. So in the abstract, whenever you have variance, stuff isn't where you want it to be, or it changes shape while you're handling it, or just you have suppliers who you cannot get to be consistent in shape or color or size or rigidity, wherever you have some kind of variance like that. But you do think mechanically the system is solvable, the problem is solvable, right? Sometimes with a two-finger gripper, which, if we're honest, is the only type of end effector we want to, we're not going to use hands for a couple of years in industry. They break too easily, right? So with a simple two-finger gripper, if you can solve the problem at all, if it would just move right, and you have variance to deal with, then it's worth thinking about using our product. Okay, what might that be? So that's bread and butter stuff. Bread and butter stuff is things like you want to, put in a bolt somewhere, and the hole that you put the bolt in is in a slightly different place every time. Maybe you're on a conveyor and your sort of fixture that moves with the conveyor is 20 years old and not precise, and you want to use a robot anyway. Maybe stuff is in a blister and the blister gets soggy in summer because everything's warmer, and it's in a different place where you pick it up. Maybe you have a bunch of styrofoam, and when your conveyor stops, stuff wiggles a bit, and it never stops in the exact same place. Maybe what you're handling is a cable, and there's no way to get it to be in the same place for every part, right? Maybe there's a cable. So let's say you're making, I'm not saying this is an application we did for a customer, but maybe it is. Maybe you're making a refrigerator, and there's a cable hanging out of the back of it. And you want to plug it in and see if it turns on at the end of your line. So today, that's a human, because there's no way to reliably grab that cable and plug it in. And using our product, you can totally just sort of find the cable, follow the cable to the plug, pick the plug, put it in, see if electrically something happens, and put it back and move on. So that's something where sort of in the old world, everybody would have said, oh, okay, crazy. Either this is a highly complicated mechanical contraption where we sort of move the fridge along this mechanical thing, and then it catches the cable, and when we pull it up, and then there's a linear axis that pulls it, and then there's a thing that orients it, and but that's what we would have built. So there's a humongous machine that tries to catch the cable and define its orientation, so you can do something with it. With our product, you just teach it to find that cable, grab it, and plug it in, and it works, and it works every time. So yeah. From the world of refrigerators, we do lots of testing, electrical testing. One other quite cool thing that I learned was unautomatable for a very long time is leak testing. So every refrigerator you have ever bought had a human leak test it. Because if you don't leak test it, there's a small chance of the coolant leaking out of the copper tubes where the coolant circulates. And if the coolant leaks out, two things happen. First, your fridge breaks, and second, your kitchen explodes, because this is essentially lighter fluid, and you don't want that floating around in your kitchen. So you need to find the solder joints of those copper tubes, which, because these things are built by hand, you don't know where they are. And depending how good the guy was who did the soldering, they look very different. So one of the applications we've done a bunch of times in that industry is find the solder joint, get a probe, a sniffing probe within a millimeter, and see if there's even a whiff of coolant leaking out there. And the people who bought this from us and who are running these systems have actually done the test, humans versus robots, where the robots will find more deliberately inserted bad examples than the humans do. Because the humans are, of course, very good at this, while a guy in a suit is standing next to them, watching them do it. But it is a very boring job. Holding a sniffing probe up to a solder joint for 8 hours a day is just brutal. And I mean, the people who've done it all their lives, they're kind of fine with it, but they also have real serious problem finding somebody who went to school to do this all their life.
Well, and there's a lot of jobs out there in that vein that are they're jobs only humans can do, like plugging in the refrigerator or doing the sniff test. But they have to rotate people through it because nobody would want to do that job all day. So everybody takes their turn doing the crummy job. But there's no, I mean, unless there's mechanical geniuses out there that can design anything. It's like, well, we get this little track and we'll have this thing sniff, or we can pick up the cord. And those people are geniuses. I love them. But those type of we can do anything with mechanical features is typically extremely expensive to engineer and build. And it's actually cheaper just to hire, tell everybody, all right, you get an hour a day on the crummy job, plug in the fridges in. I'm sorry, but that has to do it. And I think those are the type of jobs where they've wanted to use robots for so long and they haven't been able to, that maybe your solution is the right fit.
Yeah. And I mean, I should mention this works with cobots, right? This was developed on cobots. So this fridge testing applications, this is actually on cobots. They don't have cages around these stations. The robots are even on wheels. So this is often something where, right, if something special happens for 4 hours, I mean, you sort of run a batch that has plugs for a territory you haven't trained the robot for, they can still swap in people. Because our control system is essentially working relative to where the part is, not where the anchor of the robot is. So you can even you don't even have to precisely lock it to the station. You just roll it up and let it do its thing, because it will find the plug and then do that. So this works great with cobots. It's not limited to cobots though. We also do stuff in automotive that has these properties where you have a bit of variance that you want to do away with. Say you're gluing a windscreen to a car, a very large part, sort of detail of the orientation matter quite a lot, but your car harness isn't precise enough to just go down with a big FANUC and just press it in. You need to do a 2-degree correction there, and that is something the system does on very large industrial robots. So we don't care what the robot is. We're just a bit of math. You can use any tool. You can use any kinematic, essentially, to get you there, as long as we have a driver for it.
Yeah, that makes a lot of sense. And are there any? So cobots, I think we're familiar with them, and machine tending, I can definitely see really taking advantage of your system, because a lot of machine tending applications, the reason that they don't have a robot on them right now is because of that variability of where the parts are. But I guess, do you supply the cameras, or do you have a specification for the cameras you need to work with your system?
So these are standard boring. Don't tell the people who make them that I said they're boring, but they're boring cameras, right? They do nothing special. They give an RGB image, and they are selected for reliability and readiness for industrial applications. So right now we support two. There is a USB system by Jimea and a gigabit Ethernet system by Bauma. So these are the cameras you kind of have to use because we do real time, so we need to know about the timings and how they behave. So the system works on a $25 Logitech webcam. It's just not precise and reliable. So we have sort of narrowed the eligible range of cameras down to something that we know very well, and we know the timings of. You don't need to buy them from us. You can buy them from your favorite supplier if you have one. Same goes for the compute hardware that you put next to the robot controller to run our software on. This is just a Siemens, but you can buy the Siemens from us, or you can buy it from Siemens directly, or whatever your reseller is. The camera isn't that interesting. So often when I talk to people who've done it for a while, right, they will absolutely like to nerd out about the details of the camera. And I am sometimes having a hard time not to look bored, because I really don't care about the camera. The camera is not the key thing here. It just gives me pixels. And then if it absolutely needs to be this camera, the team will write a driver for it, and then that's it. One thing I should notice is you're completely free to play with the optics here. So the neural networks have this nice property, because we train them from scratch for every application, that they make no assumption about both the camera placement, where it is on your wrist or in your workspace. So you can do everything that works for you. So you get the pixel to know how to make the right motion, and you can essentially put any lens on there that suits your application. And there isn't even anything you need to configure in the system, because you're just generating data, and the data that you use that you generate when you give in examples, and the data that you get from the same lens when you execute is the same. So through this property, we have cases where people do almost 90-degree angles of two cameras that are very close together, very close to the workpiece. From that to sort of very narrow lenses that are fairly far away, because you have limited space into where you insert your tool into a machine or something, right? So where you need to be way back with the camera, and then you just use a very narrow lens to have enough pixels to see what's going on in the front. To even omnicam setups where you have sort of a bit of a mirror or a cone, so you see almost a full table to find a certain part that you need to. All of this is possible, and all of this gets configured only by putting the lens on and then recording data. You don't need to understand the optics of that. So often, when I talk to computer vision veterans, they get kind of sad because they are very good at this stuff, and I'm telling them, no, neural networks take care of it for you. We don't care, right? All you need to do is look at the image that your optical setup gives you, and if you as a human would know how to move, given the information that's in the image, the system will find it. The system will know how to move. You don't need to tell it how to do that. It does not do magic. The one thing you need to pay attention to is, do you see what the motion is? Do you see the feature that the thing needs to see to make the right motion? If you don't have the pixels, it cannot guess it. It needs to rely on the information that actually comes in from the camera.
No, that makes a lot of sense. And so, I don't, so was there anything else you wanted to cover? I'm thinking of my questions, but all the questions I have, I think we've already really covered. So I don't want to just go over ground that we've already talked about. Was there anything else we should discuss about your solution here while we're on the call?
Yeah, I mean, let's briefly mention the already supported robot platforms. So this works on URs, all of them. If you want to go cobot, it works with a large part of the FANUC range. All the common robots by FANUC, including the cobot, the CRX, works. Sometimes, if you bring a more exotic one, it takes us a couple of weeks to put the kinematic parameters in, which is essentially what we need to do for the FANUCs. And all the KUKAs work. Full range of KUKA industrial robots, not the cobots, but the full range of industrial robots from KUKA. Some of the other platforms that you would typically use are essentially, we know it will work. We're discussing Kawasaki. We have done ABB in the past. So depending on where the business is, we'll be able to add more platforms quite quickly.
All right, great. Yeah, Universal Robots, they have a big lead in the cobots. We do cover ABB, KUKA, and a lot of the other cobot manufacturers out there, and other robot systems out there. So well, that's good to know, and I appreciate you coming on the show. I'll probably be thinking about this for a couple of days, thinking of how cool it is that what you guys are doing, and how there's going to be all these poor souls out there who no longer have to plug in the refrigerator manually all the time. And people have been like, "Yay, that job is gone. The robot can do it now." So, Ronnie, I have nothing else for you. Was there anything else you want to cover before we call it a show?
Yeah, let's stay on that for 1 second. Why do people do it, right? Why do people? I mean, I guess with your audience, everybody's an automation person anyway, so I don't need to sell the automation. But let me just mention the reasons people do it is not typically cost. Right? People aren't doing this to save money. It's often a nice side effect. But many of those cases that we see, people want to use a robot for consistency, for predictability of results, even for ergonomic reasons, right? Putting in bolts above your head is no fun for everybody, for anybody ever, right? This is just horrible. So
Yeah.
there are really a lot of reasons beyond cost to do this. We don't look down at cost cases. That's also fine. But there's really a wide range of reasons to do this. And some of our customers do have cost cases that are very attractive, where you're essentially replacing. We had one case where we were replacing, I think, a 2-shift setup with 4 robots. So this is 8 people, 4 robots. They had a bit of fluctuation on the people who were doing the job because it wasn't fun. So there's sort of a lot of cost you need to add to just the salaries of those 4 people because you needed to keep the station manned all the time. So I think buying the robots, our system, and doing the engineering, they still had ROI on that use case after 3 months.
Wow, 3 months is really, really good. And
We're not
there's a
always as
safe,
good. Yeah.
yeah, well, there's a safety issue when it's a very boring job because it's hard for a person to concentrate on something so simple and so boring that it's easy. And I know from my personal life, it's easy, when you're doing the same job all the time, be, super safety after, months of making the same repetitive motions. It's easy to get distracted and let your mind wander. And yeah, personnel is one of the most expensive people. One of the Personnel is one of the most expensive costs a company has. So if you can relieve your high-paid personnel from doing such a menial but needful task, that's a win-win. And I imagine the ROI is usually within a year or so.
Yeah.
I'm sure not everyone is, but yeah, I can imagine it's usually within a year's salary.
I mean, we have customers who say, I don't even care, right? If you can, I can't hire the people for this job anymore.
Oh, absolutely.
I mean, there are situations that we saw where they said, people aren't coming in for the night shifts anymore. I do not get people to do night shifts. However, I have a paint shop and I need a paint shop for this. So the only way to increase my output is build another paint shop. I don't have the money for this, right? So they're in a situation where they need very expensive infrastructure to double their output during the day. And if they want to keep the lights on during the night, they need to automate. So there were customers that told me, if your ROI is 5 years, I still don't care, because it still means I don't need to build another paint shop to even keep my output stable. So there is good reasons to do that now. And I mean, cobots are changing the game already. And technology such as ours is changing the game. It's not always easy, right? This is often, these are cases that aren't standard automation stuff anymore, right? You're going beyond what your engineers are used to doing. There's a bit of a learning curve to just trust a system like that. So I like to compare our product to sort of a powerful tool of wizardry. It doesn't do magic instantly. You need to become a wizard, right? You need to learn how to give it data. But then once you've learned it, everybody will think you do magic because you're doing things that nobody else has ever thought of doing very quickly.
Catch all the different possible instances for the job, and then your system fills in the gaps so it can do work with all those. And yeah, that makes sense. Reminded me of like Harry Potter and the wands. Just having
Yep.
a wand didn't make them perfect. They had to learn all this.
They had to
The,
do the wiggling and whatever it was. Yes.
yes, yes, it did. And so yeah, and you got to do it in different lighting conditions. If the light changes throughout the day, if you don't have a light there, if the part changes, the color of the part changes based on whatever, all these different things. But once you get those in there, your system, the neural net, can extrapolate between all of those and give you the solution as you're honing in the plug in that whatever that part is, or do whatever you need to do. And so that makes a lot of sense to me.
The teams at our customers that have done this the longest, this is typically large automotives, where there's typically one team of people who initially found us and started to do it. These guys are better at doing skills than our own engineers. They're getting so good at this because they're doing it under real conditions in the real factory, solving problems we have never heard about. So it's really, sometimes they show us things they've done with the system because we don't look at their data, right? It just passes through the algorithms. And we will look at it. This is possible. Okay. This was bold. Very good that you made it work. Very impressive. So yeah.
Yeah, those are the best
These are our
customers. Yeah.
favorite customers, obviously, right? Who
Yep.
surprise us by their skill with the system.
Yeah, and every engineer knows that an operator can show him something that he never thought would happen, usually within 5 minutes. So,
Yeah.
yeah, that type of feedback is priceless.
Yeah.
Yeah. So, was there anything else we wanted to cover?
I think we're good.
All right, Ronnie. Well, thank you very much for coming on. I really enjoyed talking to you, and you have a very interesting company and product, and I hope everybody who's watching will go check out their website. I'll put it up on the screen if you're watching the video right now, and we hope to get the links in the description before it releases. But Ronnie, thank you again for coming on the show, and I really appreciate your time today.
Thank you very much for the invitation and a very engaging conversation. Thank you.
Well, I hope you enjoyed that episode, and I want to thank Ronnie from Micropsi for coming on the show. I also want to thank his company for sponsoring this episode. making it completely ad-free. Wasn't that great? If you did enjoy this episode, though, please give us a like and consider a sub and a share. You know, the likes that you give our show is really the only way we can grow our audience and find new vendors to come on the show. So if you do enjoy it, please give us a like and consider giving us a sub and a share. Now, if you guys want to connect with me directly on LinkedIn, you can do so. My username is Mr. Shawn Tierney, Mr. Shawn Tierney, and you should be able to find me there. You can also find Insights in Automation, my company, up there. If you know anybody looking for PLC, HMI, or SCADA training, please send them over to theautomationschool.com. I not only do online courses, which I've been doing for over 10 years now, but I now also offer in-person classes. I just had a Rockwell class last week. Next week, I'm doing a Siemens class. So if you want to get some in-person training, I typically can train 4 people for 4 days for less than it would cost you to send one person to the factory for 1 week. So it's a much better deal, in my opinion, and they're custom. I'll cover whatever you want. As long as I know how to use the product, I'm more than happy to cover it. So with that said, I want to wish you all an awesome week. I want to wish you good health and happiness. And until next time, my friends, peace.